So, good afternoon, everybody. Welcome to today's NCCAV seminar. Today, we do have the pleasure to have Mr. Robert Akini to be the presenter. His presentation title is Federated Learning-Based Intrusion Detection Systems in the Autonomous Vehicle Systems. There's a background noise. Sorry, I'm going to stop here for a second. Okay, so a little bit about Mr. Robert Akini. He's active researcher, PhD student at CCAV Center of Excellence. He's working with Dr. John Kelly, who is as his advisor in Electrical and Computer Engineering Department. Before joining our PhD program, Robert received his bachelor degree from in Electrical and Computer Engineering from Calvin University in Michigan in 2021. His research interest focuses on federated learning, autonomous vehicle architecture, embedded devices, and of course, cybersecurity and intrusion detection. With that, I'm gonna passing it to Robert.
Hello, everyone. Can everyone hear me?
We do.
Okay, so thank you so much, Dr. Karamudini, for the introduction. So I'll get started right to it. So today, for today's seminar, my presentation will be a talk on federated learning-based intrusion detection systems in the autonomous vehicle ecosystem. And so for the outline, I'll be giving some small background on federated learning, cybersecurity, and then intrusion detection systems. I'll provide a little motivation as to why federated learning became a thing. I'll be providing a little bit of information on the federated learning framework. And then based on the the above three important points, you will get to have a little bit information or highlights about federated learning based intrusion detection systems. I then provide some challenges, and then I go on to provide an edge device implementation that addresses some of those challenges, and then what I am currently working on. So, in today's increasingly interconnected world, where reliance on digital infrastructure is paramount, cybersecurity plays a vital role in ensuring the confidentiality, integrity, and availability of information. Advances in machine learning have driven diverse applications, especially in Internet of Vehicles. On-device machine learning, enabled by the improvement in hardware and model optimization, has transformed artificial intelligence deployment, notably in the transportation sector, with connected and autonomous vehicles, as well as other intelligent transportation systems. Connected and autonomous vehicles enhance the safety of vehicles and traffic flow by sharing relevant data. But this connectivity raises security and privacy concerns like cyber attacks and data breaches, which necessitates robust intrusion detection systems. Cybersecurity encompasses a wide range of technologies, processes, and best practices designed to safeguard sensitive information and maintain the integrity of computing environments. So it refers to the practice of protecting such systems, networks, and data from digital attacks, unauthorized access, and damage. Some of the importance of cybersecurity include the autonomous vehicle connection and reliance on technology, increasing threat landscape due to connectivity, and as well as the trust of the public in ensuring regulatory compliance in the autonomous vehicle industry. So a little bit of background on autonomous vehicle architecture components. The architectural components of autonomous vehicles are intricately designed to work together seamlessly, ensuring safe and efficient operation. At the core are sensors, which collect real-time data about the vehicle's environment, including obstacles, road conditions, and traffic signals. This data is then processed by your control systems, which utilize advanced algorithms and artificial intelligence to make rapid decisions regarding navigation and vehicle dynamics. We also have our communication interfaces, which play a critical role by enabling vehicle to vehicle and vehicle to infrastructure communications, allowing for coordination and enhanced situational awareness. Now, there's the threat landscape that comes in with autonomous vehicles, which includes uh, physical attacks, remote exploits, software vulnerability, data privacy and surveillance risks, in-vehicle network attacks, denial of service, as well as adversarial machine learning. Cybersecurity is critical in the autonomous vehicle domain due to its profound implications for passenger safety and data integrity. And as these vehicles rely on an intricate network of sensors, software, and communication systems, any vulnerability can expose them to significant risks. A cyber attack could allow unauthorized vehicles to manipulate vehicle functions, leading to dangerous outcomes such as loss of control, accidents, or even hijacking. Moreover, these vehicles collect and transmit vast amounts of personal data, including travel habits and preferences, making robust cybersecurity essential in safeguarding user privacy and prevention of data breaches. So, therefore, in order to mitigate these threats, intrusion detection systems have emerged as a critical line of defense, actively monitoring and detecting anomalies within these environments. So, what is an intrusion detection system? It is a vital cybersecurity tool specifically developed to observe and evaluate network traffic, to identify any malicious activity, and continuously monitoring the network environment for atypical patterns or behavior that could signify that could signify that could signify a security breach or unauthorized entry. Upon detecting suspicious activity, these intrusion detection systems then provide alerts or notification, facilitating relevant personnel's rapid investigation of and response to any security issue. Types of intrusion detection include host intrusion detection systems, which focus on your specific device monitoring within a network. And then we have the intrusion detection system that focuses on your network as a whole. Some of the techniques of intrusion detection include signature-based detection, which recognize known attacks or signatures in your data streams or networks. And then we have anomaly detection, which monitor only the system behavior to identify deviations from normal operations or patterns. And then we have hybrid approaches, which is combining both anomaly and signature-based methods for enhanced detection capabilities. So for our motivation, because of things that are happening, such as your increased significance of the risk of data breaches, as well as challenges related to connected and autonomous vehicle architecture and networks, Google introduced federated learning to facilitate on-device learning while ensuring the preservation of data privacy. So to sum it up, federated learning supports collaborative learning without sharing raw data, which preserves your user privacy in distributed systems. Specifically in your autonomous vehicle ecosystem, it supports these vehicles or the ecosystem in conducting collaborative learning by localized model training or respective vehicular sensor data while ensuring data privacy and security. So, in any internet or vehicle network requirements, we look at there are three specific things we need to look at, such as your security requirements, your data privacy, and then your system capabilities, of which I will address later on. So, in a typical federated learning framework, there is a collaboration of multiple entities, or in this case, clients, to train machine learning models without the need to share their raw data. And the outcome is a model for each participating client for whatever downstream task that each client needs to perform. Federated Learning Framework components. So for a typical federated learning framework, some of the components are listed below, such as client devices and local models. Now, your client devices would include in a general federated learning framework, your client device will include things like your mobile phones. And for autonomous vehicle architecture, we are talking about vehicles. And then your local models, which are embedded within these clients that are used for any downstream task, such as it could be image classification, it could be intrusion detection. Server and global models. So for each federated learning framework, there is a server that coordinates the activities of your clients and then takes in data from your clients and then aggregates them. So it aggregates the data that's been sent by your client into a global model, which is then sent back to these clients, which can be used for any downstream task. This aggregation is performed via model aggregation algorithms, such as federated averaging. So now, in order to describe what is happening in Figure 5, you have a server that generates a generic model or a random model. That server would have your number of clients, K, and then the number of rounds, R. So for each round of federated learning training, the server distributes the initialized global model to your clients. And for each client, you perform a localized model computation, whereby the localized here means that each client has its own respective localized data that is fed into a model. So each client here, after training, would be able to develop its own localized model, which is then sent back to your server for aggregation. What the aggregation here does is it generates a global model which has characteristics of all the client's localized data without the client sending their actual data streams. So what the clients do is they only send what they learned from training and not the actual data to your server. So that is how a typical federated learning process goes, where you have a global model initialization by your server, and then you have your model distribution from your server to participating clients. The clients then perform localized training using their own respective data, and then they do the update back to your server. And then your server just aggregates or adds all these model updates into a global model. So from point 1 to 5 is typically referred to as a federated learning round. And so your iteration here means your federated learning framework happens again and again until you have a convergent global model or until a predetermined early stopping point. So to give some highlights about federated learning-based intrusion detection systems, the integration of federated learning into intrusion detection systems is driven by the growing need for enhanced security and privacy in our increasingly connected world. Federated learning presents a promising approach to developing privacy-preserving intrusion detection systems by enabling decentralized model training across distributed edge devices without the sharing of sensitive data. So the motivation to adapt federated learning to intrusion detection systems, especially in the connected autonomous domain, remains as follows. I mentioned decentralization and edge computing, where the utilization of federated learning facilitates decentralized learning, which aligns with edge computing principles, where data processing occurs in close proximity to its origin. Robustness and fault tolerance. We also have the federated learning also enables continuous learning, which is essential to threat evolvement. And what that means is each client would eventually um, encounter new threats. And in order for other clients to be able to know or learn from that new threat, federated learning allows your clients to continually learn by training on those new threats, updating it to the global model, which is then shared to other clients. So other clients or other devices are able to know and then address these new threats without having ever met them. There's also privacy preservation, which is the protection of individual or device data privacy. And then data efficiency, whereby rather than transfer all the client's data to a centralized server for processing, you only get to transfer what the client learned, which is a lot less data and a lot more data efficiency. For scalability, federated learning has shown that it can be scalable to a lot of clients from one to, I guess I'll use the number 1,000 without degrading its performance. So highlights about federated learning based intrusion detection system. We then ask, how does a federated learning based intrusion detection system work? Your local model training is basically replaced by an intrusion detection model. And your clients would have data such as network traffic and system logs. Your clients are then going to perform collaborative threat detection, which I mentioned earlier, which is leveraging threat data from multiple clients and enhancing each client's ability to detect novel attacks. We talk about challenges in federated learning-based intrusion detection systems in vehicular edge computing. So some of the challenges that arise from federated learning-based intrusion detection systems are as follows. We have resource constraints whereby for edge devices, there is not a lot of resources. And so there's limited computational power, memory, and energy resources, which restricts each client's ability to perform complex on-device model training and inference tasks. These resource limitations are enhanced by the need to share resources with multiple concurrent applications, such as real-time navigation, safety systems, and infotainment, likely impacting user experience. So, for example, if you are in a vehicle and you are using the vehicle for navigation, I mean, you are using like the GPS for navigation. We need to be able to develop an intrusion detection that will not be able to impact the experience you have whilst using your let's say your Google Maps or your infotainment system such as music and all of that. Reduction in overall performance increases the likelihood of compromise on intrusion detection systems ability to perform real-time threat detection. There is also the issue of communication overhead, whereby because you have localized training from each client will then have to periodically send their whatever they learned to your central server, which can lead to delay in sending your messages. and increased bandwidth consumption, especially in large scale systems. And even though federated learning prevents the sharing of raw data, which increases your data privacy, there are additional security risks, such as model poisoning, whereby compromised clients, or in this instance, compromised vehicles, can share malicious model updates to corrupt your global model. This requires additional measures like secure aggregation or differential privacy to ensure model integrity. So, for my objective, it is in developing a robust, resource efficient, and secure federated learning based intrusion detection system that addresses the challenges of client resource usage and mitigates security risks in distributed and high risk environments. So far, I have been able to do an edge device implementation of a federated learning based intrusion detection system that focuses on mitigating or reducing your resource usage. In this instance, I'm looking at the memory usage of my model. So in figure 6, I have my proposed framework whereby my model training is shared by both my aggregation server and clients. For a typical federated learning framework, your training is only being done by your clients and your server does only model aggregation. So in this framework, we have a server that also takes part in initial training. So for my deployment setup, I use a Dell Precision Tower with Ubuntu as my server. And then my clients are the small devices in figure 7, Raspberry Pi 4s, also with Ubuntu and PyTorch for deep learning framework. For my federated learning framework, I use Flower. For data sets, I have only been able to use NSL KDD, which is a benchmark intrusion detection system data set. And even though it is not an autonomous vehicle specific data, some of the relevant classes include denial of service, which provides traditional network, which are relevant to securing vehicle to everything communications and can be adapted to your connected and autonomous vehicle framework. For my intrusion detection model, which is on figure 8, I have two blocks or two modules. We have the 1D convolutional block, which is the pre-trained portion on my server. And then I have the fine-tuned portion, uh, which will only be fine-tuned on each client. So for training details, the server pre-trains on the pre-trained model for 10 epochs. And after your training, the parameters that you get are then extracted to Flower, which then distributes these parameters to each of the clients. The clients then perform continuous localized training on only the fine-tuned module instead of the whole model for 5 epochs. The resulting model parameters or weights are then sent back to your server for aggregation. The fine-tuning is performed with stochastic gradient descent and batch size of 32. So for this deployment setup, I did it via a local area network and then a remote procedural call for communication between server and client. And the iteration is done 3 times, or should I say, for 3 federated learning bounds. So for evaluation, I look at performance metrics such as my intrusion detection system, model test accuracy and loss. I also look at the training memory consumption and also the training execution time. For comparison, I compare it to a centralized intrusion detection system whereby I look at the results of an IDS model on only one client. I also compare it to a state-of-the-art Federated Learning intrusion detection system. For scalability, I look at the client device performance when I have a number of clients. So these are the current results that I have. In table 1, you can see the comparison with centralized IDS, the state-of-the-art Federated Learning intrusion detection system. And then I have two comparisons of my framework where I fine-tune the last 3 layers, which is of the fine-tuned model, as well as the last layer of the fine-tuned model. For table 2, I have evaluation results for scalability, where I look at the average client performance for a number of clients. So we have 4 clients, 6 clients, and then 7 clients. So for my observations, I notice an accuracy and memory usage trade-off where the less resources that the clients use, the less accurate their corresponding intrusion detection performance is. There are also fluctuations in memory usage which correspond to other background processes, which kind of tally with me earlier saying that we do not want an intrusion detection model that would be able to impact other concurrent tasks in your vehicle. For scalability, I have been able to address the scalability limitation where the number of clients does not matter. The average client performance remains steady or remains the same. And so my federated learning framework is scalable. So in this figure here, I show on the left, I show the real-time memory usage of my clients. And the shaded portions here show the memory usage of my training function, whereby on the right, if you look at line 65, it shows the amount of memory that is used by my training function. So if I zoom in into one, so for the left side, the 3 parts shows the 3 federated learning rounds. When I zoom into one federated learning round, here you can better see the memory usage fluctuations. Your peak memory usage just shows the other background process that start up when you uh, instantiate your client or your server training. And the highlighted portion, as I mentioned earlier, is the train function, where you can see the spike that shows the amount of memory usage that your train function uses. And in this figure here, you can look at how I start my training. I call the server, and then I give it the number of rounds the server is supposed to train for with a number of epochs. And so after it has done the initial pre-training, it sends your parameters, your updated parameters to your clients. And so for each round, you have clients that are doing localized training with their own respective data sets. And then they upload your model updates back to your server. And so after that, it provides a summary of your loss and then your accuracy. So for current directions, I'm looking at generating connected autonomous vehicle specific data sets, which would then show a much more accurate model performance. as related to the autonomous vehicle ecosystem. There is also the issue of resource heterogeneity. So, what resource heterogeneity means here is different types of resources or devices. So, in the autonomous vehicle framework, we will need to develop a framework that caters to different kinds of vehicles with different kinds of sensors. And so for my implementation on the Raspberry Pi, I'll be including other edge devices such as NVIDIA Jetson. We also need to look at how my model consumes energy. And also for increased security measures, we look at implementing a differential privacy mechanism. From there, I look at specific intrusions such as GPS spoofing, whilst including federated learning. So, what GPS spoofing here means is attacks by malicious users that manipulate GPS signals, causing your vehicles to report incorrect locations. This is particularly problematic for applications relying on accurate location data, such as autonomous vehicles, drones, and smart city infrastructure. From there, I would also be looking at injecting faults into federated learning systems for transportation IoT, whereby I look at faults like hardware and system failures, which are malfunctions or performance degradation in devices such as sensors in autonomous vehicles, and how we know that these malfunctions can introduce faults in your local data. So, for example, a faulty sensor in your vehicle can feed erroneous environmental data to the model, such as incorrect GPS or images, leading to faulty location based updates. These are my references, and I would like to thank the North Carolina Transportation Center of Excellence on Connected Autonomous Vehicle Technology for providing me with this platform to present my work. That'd be all. Thank you.
Great. Thank you so much. Thank you. And now it's time for question. So any question to Rob? So while others think of good question. So you're there. I know your research is on cybersecurity as well. So while Matthew or others gonna get ready for asking question, I will ask and share some thought here. For I think there is another student of Dr. Nguyen, who is also working on using federated learning, or especially GPS spoofing, more or less similar problem, and we are supporting him and hopefully you as well to collect real data on our actual CAV test bed. Do you see it feasible to apply your technique to that test bed as well?
Yes, I'm happy to initiate a conversation on that. I think I sent an email to Tien, but yeah, so I'll talk to him later on that.
Okay, okay, great. So any question to Robert? So can you go back to your results? Maybe that's yep, maybe here. Okay, before I ask question, there is a question in chat box. Christina, would you please ask that question?
Yes. It says, for comparison, what model did FLIDS use?
So I use the 1D. I mean, I made a 1D convolutional model with a multi-layer perceptron block on the right side. So it's just a model of 1D convolutions with max pool and then a multi-layer perceptron block for binary classification.
I think the question was about the model in reference one FLIDS. So what model they did use?
Oh, yeah, they also use a similar convolutional 1D model, but then for theirs they had only one convolutional block with another multi-layer perceptron block, which was just one. For me, I decided to add these two more.
Okay.
But then for their IDS for the general FL IDS, they just did a random server initialization of the model and then sent that model back to the client. Whereas mine, I have the server trained for a little bit and then get much more better model parameters, which I then send to the clients.
Okay. Yep. Give me. So can you comment here as far as the progress that you made and the compromise that you made? So progress and compromise that you did here, both on the performance and the time efficiency.
Yeah. So what I observed was that for in implementing my model, it uses a lot less memory for training, but because it uses a lot less memory for training, as a result of not training on the whole model, there's a degradation in model performance. But for like a 5% difference in your accuracy, model accuracy, there is almost a 65% difference in memory usage. And from the last two, if you kind of compare, you realize how your model accuracy decreases as you train on less, as the clients train on less parts of the model.
And from practical perspective, the training can be done on a sort of a more capable computing, and then the deployment is more matter here. So from that perspective, can you comment on that more?
Yes, so we also have to consider the fact that you are going to deploy other systems that are going to use that are also going to compete for the same resource, right? So we have to consider doing a model for intrusion detection that would minimally affect the other critical systems that are being deployed on that model, on that system. So I feel like regardless of, I mean, a more capable system would mean that y- it would give more leeway to you to consider other intrusion detection models that utilize the whole or that train on the whole model. But in using my implementation, you would barely notice that as compared to a regular Federated Learning intrusion detection system, you would barely notice that it is consuming any resource, even though that means that your model performance gets to decrease a little bit.
So any other question? So the data set that you're using is a public data set, at least for training phase, correct?
Yes.
And weren't other methods that you can compare and benchmark, because reference one also looks like to be a reference from same group. Do you think that there might be other models that you can consider for your benchmarking?
Yes.
So, yep. Okay. So, any other question?
I have a question, Robert.
Go ahead.
Thank you for your presentation. Quick question on your data set. Is it an IID dataset or an IID dataset that you considered?
It's an IID data set.
Oh, okay.
Yeah. Well, part of the things that I'm looking at, or part of the issues with federated learning is in real life you get to deal with non-IID data sets, and so your performance can be a little different. That is why if that is why I'm looking at CAV specific data sets in that are generated in real life, and then you use that to see the intrusion detection system performance.
Okay, thank you.
Yeah.
Okay. So I think looks like that all questions. Or is there any other question before we are joining today's meeting? Okay. If not, let's join me thank the speaker. Thank you so much, Robert, and we enjoyed the talk, and wish everybody a great weekend. Thank you so much.
All right. Thank you.
Thank you.